Okay, so let's get started. Uh, um, Now, you guys remember when we talked about mutual inductance? Mutual inductance was when you have two circuits in close proximity. Changes in current in one of the circuits was inducing an EMF in the second circuit. Okay, and that coupling strength was called the mutual inductance. How strong is the coupling? Now the coupling depends on the separation of the distance between the circuits and all, and it's very hard to calculate. So here's one configuration where you can actually calculate the mutual inductance. Okay, so you'll see a problem where you can calculate mutual inductance. Okay, so the problem says two coils close to each other have a mutual inductance. Oh, not this one. Yeah, so there'll be one configuration where we can calculate the mutual inductance. So two coils close to each other have a mutual inductance of 32 millihenries. If the current in one coil decays according to that, where I naught is 5 amps and alpha is that, by the way, this is about half a millisecond of time constant. What is the EMF induced in the second coil immediately after the current starts to decay at t equal to 1 milliseconds? Okay, so
we set it as a function of time and then just plug it in?
yeah, exactly. So EMF in the second one due to changes in current in the first circuit is, maybe it's written E12 minus M12 di1 dt. Okay, what we are saying is, maybe here's a better notation. Okay, so what this equation is telling you is the following. Due to changes in current in the circuit 1, you're inducing an EMF in the circuit 2. And M12 is the mutual inductance. The sign is related to the direction of the EMF and all that. We won't be worried about that. We are not concerned about that right now. All we want is the magnitude of the EMF in the second coil. Okay. So what we'll do is we'll do this. Okay. All right. So now what does it say? The current in the first coil is I naught times e to the power of minus alpha t. What is the EMF induced in the second coil? Okay, so we'll call this part A, and the EMF induced in the second coil is M12 di1. Okay, we'll just take the absolute value of that. And I'm going to write I1 is I naught e to the power of minus alpha t, and di1 by di1 by dt is equal to minus alpha I naught e to the power of minus alpha t.
So what does alpha stand for?
Okay, so in most formulae you've seen this as it's written like so, tau. So alpha is equal to 1 over time constant, and since alpha is so tau is is 1 over alpha, and alpha is 2 times 10 to the so here's a good exercise. 2 times 10 to the 3 inverse second, which is 1 divided by 0.5 into 10 minus 3 seconds. So the time constant is 0.5 milliseconds. So that's what that stands for. Okay. So everything in this problem is changing over a time scale of half a millisecond. Okay. So that's what you want to keep in mind. All right. So let's add a page. Okay, so what is it that we're calculating? So we have di by dt. We want, okay, for part A, what we want is the EMF induced in the secondary coil immediately after the current starts to decay. That means at time t equal to 0. That's what we want. So EMF at t equal to 0, EMF equal to M12 di1 by dt. M12 will write, and they give you the value of M12. The mutual inductance is 32 millihenries. Okay. So I'll write that in a second, but M12 and di1 by is minus alpha I naught e to the power of minus. Okay, now we can put in all the values. 32 millihenries, and alpha was 2 times 10 to the 3 second inverse. I naught was 5 amps, and e to the power of minus alpha t equal to 0, so times 0, this is 1. Okay, and this is an EMF, so all those henries, amperes per second is a volt. Okay, so this guy is 1. This kills that. 32 times 2 is 64. 64 times 5 is 320. Okay, so 320 volts. That's a non-trivial voltage. Okay, so what we are saying is, here's a circuit. Here's circuit 1. You switched it off. The current in this thing is exponentially falling, and the instant you switched it off, you induce a 320 volt EMF in this thing. And imagine if these are two machines, that 320 volt probably can turn off this machine, or whatever. It can mess with it. So, you know, nothing to sneeze about. All right, so we'll do part B. Let's see what is the so part B, we are doing the same calculation, except that we are doing it after 1 milliseconds. Okay, so remember, everything is happening over a half a millisecond, so 1 millisecond is 2 time constants. Okay, so we'll see what is the effect after 1 millisecond. All right, so t equal to 1 millisecond. (32 millihenries). Alpha is 2 times 10 to the 3 over a second, 5 amps. E to the power of minus 2 times 10 to the 3 times 10 minus 3. Okay, so everything is the same as in the previous case. This was 1. Now this is e to the power minus 2. So all this factor we calculated last time was 320 volts. So now this thing is 320 volts times e squared, 1 over e squared. So here's the deal. What you got to realize is, at time t equal to 0, the voltage is 320 volts. After 1 time constant, after half a milliseconds, it is 320 by E. After 1 millisecond, it's 320 by E squared. After 2 milliseconds, what is it? Very good, very good, Sam. So you guys understand? That's what a time constant does. After each time constant, you either divide or multiply by e. Okay, so in the exponential things. So, all right. So this is 320 by e squared, and as usual, I've forgotten my calculator. So 43.3 volts. All right. So you see, as the current in the first circuit is decaying, the effect of it on the second circuit, because that's what we are calculating. All right, any questions before we move on to the next problem? Yep.
Move back to the problem itself. Are we able to get rid of the dt part of the function for I1 because the equation it gave is a function of time?
Yeah, we found the derivative. There is I1, you take the derivative of that, which is, this was your question that we got. So,
Oh, I see, okay.
oh, I didn't even calculate, oh no, did we? Oh yeah, there.
You did.
Okay.
I didn't notice that you did.
All right, well, I didn't notice it either.
Oh no.
All right, I was too busy yelling at you in my mind.